Okay, we're going to use the method of Frobenius to solve a differential equation using power series. So we'll find, our goal here is to find two power series solutions to a second order linear differential equation. So we're going to look at number 26 on page 230. That equation is x squared plus 1 y double prime minus 6y equals 0. So again, the idea behind this is to assume that we've got a power series solution in this form that works for this particular differential equation. We could do this by hand. But we're going to use GeoGebra to help us out because we don't want to try to make the computations a little bit simpler for us. And get the recurrence relations that we need to be able to solve for us a little bit faster using GeoGebra than trying to do it all by hand. So the idea, of course, is to be able to represent this power series in GeoGebra in an efficient manner. And what we'll do is we'll just take a polynomial representation that's long enough, if you will. We may have to go out longer to get the number of terms that we'll be asking to get, but we'll start with using a certain number of terms, and usually for our purposes, that'll be plenty. So let's switch over to a GeoGebra window. First thing we'll do for this particular problem is we'll use it as a function. We'll set up an f of x equals a sum of our c of n x to the n. The sum up variable we want to use is n. We want to start at 0, we want to use it 15. I know that we did this a little bit more complicated in class, but this command will work just fine for us. I think I introduced that sequence inside of it as well. Turns out you don't really need that. You can just do the sum of that, and it makes things a little bit more straightforward. All right, so the idea is that we want to go back and plug in this particular power series into the differential equation and get a recurrence relation to solve to give us these coefficients, the c's that we have in there. So we want to take this function, plug it into the left-hand side of that differential equation we have, and we're going to refer to that as a function as well. We'll refer to it as g. So we'll have g of x is equal to x squared plus 1 times the second derivative of f, and then minus 6 times f. All right, so what it is we want off of this thing is the coefficients, because remember this, when we plug this into the left-hand side, it's supposed to equal 0. So each of the coefficients of this power series that we've got after we simplify need to equal 0. So we'll use the coefficients command for this particular polynomial. We get a nice list of the coefficients. Remember again, it does this in decreasing order by degrees. So we really want to go all the way over to the left. Excuse me, try that again, all the way over to the right to get our recurrence relations. So we've got the rightmost one here will be our constant term. This will be the coefficient on the x term. This one will be the coefficient on the x squared term, and so on down the line. So we know that all of these coefficients have to be 0. So let's set up our recurrence relation. Let's see if we can do that easily here. Maybe I can highlight this and copy and maybe paste it so I don't have to switch windows back and forth all the time. Nope, that didn't work. Give this one more try here. Okay, let's try this. Oops, something just happened. I'm not sure what happened. Let me delete this out. Oh, there's the list. Every time I try to click on it, it goes away. Oh, goodness. Okay, let's try this. Okay, never mind. Technical difficulties here. Let me go all the way back over to the beginning here. Okay. We actually do have this in here. Let me see if I can copy it now. It's got several of these things in here for me. I'll do copy and paste, or not. Okay, we'll just have to go back and forth and write it. Okay, so going back up here again, sorry about that. We've got 2c2 minus 6c0. So we know that 2c2 minus 6c0 has to be 0. Going back over again, the next equation would be 6c3 minus 6c1 is equal to 0. Maybe I can do this. Maybe this will help. There we go. At least get them side by side, and hopefully this will make it a little faster than switching back and forth all the time. We've got negative 4c2 plus 12c4 is equal to 0. We've got 20c5 is equal to 0. We have 6c4 plus 30c6 equals 0. Let's get a few more of these. We have, let's go back over here, 14c5 plus 42c7 equals 0. 24c6 plus 56c8 equals 0. Let's do that for right now. All right, let's maximize this back out. All right, so this first one tells us that C2 has to be, what is that, 3C0. This one tells us that C1 and C3 are equal. This one tells us that C4 is 1/3 of C2, which means that's C0. This tells us that C5 is 0. This one, the next one tells us that C6 is 1/5 of C4, which means that that is 1/5 of C0. So since C5 is 0, C7 also has to be 0. And in particular, if you go back and look at the coefficients here, where we scroll over, let me maximize. We had the C5 is 0. C5 and C7 are in terms of, the C7 is in terms of the C5, so C7 will be 0. C9 is in terms of C7, so C9 will be 0. And all the odd terms past 3 will actually all be 0 in this case. So this will be your C9, your C11, and so forth. Lastly, our C8, what is that? 24 over 56 is 3/7 C6. And that'll give us 3/35 of C0. So now we know what our two power series are, because one's going to be in terms of the C0s and the other one's going to be in terms of C1. So we'll have our y will be C0 times 1 plus 3x squared plus x to the 4th plus 1/5 x to the 6th plus 3/35 x to the 8th, and so on. And our C1 will just be x plus x cubed, and that's it. There isn't, it actually is a honest to goodness polynomial here, because all of the odd coefficients are all 0. So we just get an x plus an x cubed on the last one. So that's the idea behind getting the power series solutions using the method of Frobenius.